you for joining us today. So today I'm actually not going to talk at all for this introduction because Sarah, Aaron, and Brian are going to do all the work. They're going to present some work that they've been doing in my research group over the past few months. And the general idea of that work is to build an electronic circuit that reproduces the phenomenology of a quantum device. And so we've been working very hard on this, and they all contributed to every part of the project. So now I'll hand it over to Aaron for the first part of the talk.
Okay, and I'm going to try to get, okay, so I think I have control now. All right, well, hi everyone, I'm Aaron, and I'll start us off by just giving us some background on Josephson junctions and the circuit we'll be working with. So, there we go. Okay, so we'll start off with superconductivity, and basically the hallmark of superconductivity is that in a superconductor, as we drop the temperature lower and lower, we're going to hit a critical temperature at which the electrical resistance drops to 0. And this is, of course, in stark contrast to a normal metal, which drops towards a finite resistance. And the reason for this is that in a superconductor, we have all the electrons will settle down into one. I'm not sure what the screen is doing here. I'm sorry. Okay, so all of the electrons will settle down into one macroscopic wave function given by some complex function like this. So we have an exponential e to the I phi, where phi is our superconducting phase. And so what this basically does is that as a collective wave function, none of the electrons act individually and nothing can be scattered. So we have 0 electrical resistance in this regime. So for Josephson junctions, this matters because we form a Josephson junction by taking 2 superconductors and sandwiching some weak link in the middle. So in this case, we're showing a semiconductor. And what this does is the wave functions of the superconductors will decay into that gap exponentially and induce superconductivity in the material in between, allowing us to flow supercurrents through it. So if we look at the electronic properties of this junction by taking an IV curve of it, we find the curve in red here. And if we were just to plot an IV curve for some normal resistive material, we'll see this dotted line in blue. So for normal resistive material, you'd expect it to behave ohmically. So think about Ohm's law, we have V equals IR. So by plotting V versus I, we get a slope of R as the resistance. So it's pretty normal. But for the Josephson junction here, we get this flat part in the middle at 0 voltage. And since it's flat, it also has 0 resistance. And what this basically means is that we're flowing a small enough amount of current. So between negative I sub C and I sub C, the critical current, we're flowing a small enough amount of current that the junction can remain without voltage. But when we try to flow more current past I sub C, we're going to have a voltage appear suddenly, and then it'll return to normal. At this point, it has basically given up on being superconducting and returns to just becoming a normal material. And so the Josephson equations that predict the current and voltage across such a junction are given here. We have the current is the critical current times sine of the phi, which is the phase difference between those 2 superconductors. And then we also have the voltage is a constant times the time derivative of the phase. So the very important part of this, so important that it's in red here, is that if there is no change in the phase, we have no voltage. So changing phase gives us a voltage, but otherwise we are in the superconducting regime. And so in the real world, we don't just have a junction, we also have a shunting capacitance and resistance across that junction. And so when we take those into account, we get the equation given here. And before you say, big scary equation, you probably recognize this equation from intermediate physics, because this is the same equation as a pendulum. I'll get to that in just a second. I'll explain a couple of these a couple of variables real quick. So the omega naught here is the junction's frequency. So that's the phase vibrating. So it's that frequency. Q here is the quality factor related to the damping of the junction. I'll get to that again in a couple minutes. So going back to the pendulum, right? This is the pendulum equation we saw in probably intermediate physics or classical mechanics, where the pendulum is given by a nonlinear differential equation, and we have a DC and AC applied torque to it. Now, the interesting thing is, since we have a system that's described by the exact same differential equation, just up to different constants out front, the phenomena that we see in one system are going to have equivalent phenomena in the other system. So in this case, any intuitions or phenomena you expect in a pendulum, you'll see the same thing in a Josephson junction, which is kind of useful in just understanding how it's going to work. We also have another equivalent system, the voltage controlled oscillator, and that's what the basis of this research is on. So we'll get a little bit more detail on this. So to make our voltage or controlled oscillator circuit, we took a voltage controlled oscillator here and put it in an op-amp feedback loop with a shunting capacitance and resistance. And so what this does is it simulates that same differential equation, and the output here is going to be proportional to the time derivative of phi. We also, just to mention, have the voltage here being proportional to the sine of phi. So if we get into a little more detail on what this VCO is, we have the full circuit, which is, yeah, it's big. So down here in the bottom right, we have what was shown on the last slide, which is that op-amp with the shunting resistance and capacitance. We also have the input voltage over here, which is just coming from a voltage adder where we have an AC component, DC component, and noise, which Sarah and Brian are going to talk about the effects when we vary these different inputs a little bit later. But the part I'm going to talk about a little more is all of this awfulness in red, which was that innocuous little box that said VCO. So this is broken up into three main parts. We have the part that generates the square wave. We have just the integrator circuit to turn the square wave into a triangle wave. And then we have the triangle to sine converter, where the work is being done, at least in practice. What we're talking about is the paired differential transistors here. I'll speak a bit more on that in a couple slides. So the VCO, first part, to generate the square wave, we just use a couple of Schmidt triggers and voltage multipliers to generate a square wave with frequency proportional to the voltage applied. So basically what you'd expect of a voltage controlled oscillator. We run that then into just the simple integrator you saw there with the op-amp and the capacitor going across it. And that just integrates the input, taking high values to positive slopes, negative values to negative slopes. And that's pretty much that. The last part is the triangle to sine, which is a little more complicated, and it uses those paired differential transistors to start clipping off the tops and bottoms of this sine wave here and round it into a triangle, or triangle wave and round it into a sine wave, sorry. So the output we're going to get out of this, so here's a couple of test outputs. The two things to notice about this is, one, a sanity check, it does look sinusoidal, so that's good. The other thing is that since we're applying 0.2 volts and then 0.5 volts, we notice that the frequency does change roughly how we'd expect. You know, we apply a higher voltage, we get a higher frequency, which is, of course, what we're going for, so that's good. A little bit more information on that triangle to sine wave conversion. Why we're using the paired differential transistors is that the voltage across the output here is related to the voltage at the input by hyperbolic tangent. And why that's important is if we go back to these old-fashioned Taylor expansions, which you never thought you'd use again, and you always use more. If we look at just the first few terms, we see that they're very similar in just the relationship between the two series, which means if we can model the output voltage using hyperbolic tangent, we're going to be forcing it to be a lot more like the sine wave. And so we're just taking the triangle in and clipping it a bit and filtering out some of those higher harmonics. And to speak of higher harmonics a little more, we take some test data here just to explore what we mean by shaping it into a sine wave. So a triangle wave and a sine wave as some very basic example data with a frequency 1 Hertz, just because. We run this through fast Fourier transform to get our frequency spectrum. And for the triangle wave, we see main frequency along with multiple higher harmonics. And for the sine wave, we see just one pure frequency, as we'd expect from a sine wave. Now, if we go to look at the actual data, so the fast Fourier transform of an output wave from the circuit, we see we do still have some of these higher harmonics, which you'd think, that's not really a great sign, but we've plotted this in log scale. So if you see, we have 2.5 orders of magnitude suppression, which is about 300 times smaller. So although we do still have these higher harmonics, they're heavily suppressed, and we can say that our output wave is essentially just a sine wave. Another thing I'd like to bring up with this picture is that in this specific sine wave, we put in 1 volt, and we got out this as our main frequency. So we can use this as just a nice test of our voltage to frequency gain. So in this case, we get out about 1900 Hertz for that 1 volt. And so we have a voltage to frequency ratio of 1900 Hertz per volt. A better way to check this is by sweeping our voltage across, so say -2 volts to 2 volts. And if at every point then we extract the frequency and plot this versus the voltage, we get the linear relationships that we would expect from this, because the frequency of output of the VCO is expected to be linearly related to the voltage input. And we can fit these just with a line to get the voltage to frequency ratio, again, is about 1900 Hertz. So moving back to damping, if we consider the circuit as a whole again, the one last thing I want to talk about is the quality factor. That's Q here, and that's related to the damping of the circuit. So if we consider a pendulum and consider how the pendulum moves, if you say strike it, you strike the pendulum and it oscillates for a long time until it finally settles back to equilibrium, you'd say that it is underdamped. There's not a lot of damping, and it has a Q factor greater than 1. But if instead you strike the pendulum and it just drifts back down to its equilibrium without oscillating, we'd say that it is overdamped and it has a Q factor less than 1. So how we'd extract this from the actual circuit here is we kick the circuit by inputting a step voltage to jolt the circuit and watch the oscillations of the output as it settles back down towards equilibrium. And we measure these in Python and extract the Q factor from that fit of the decaying oscillations. So that's just to fit the decaying sine wave, sorry. I think now I pass it over to Sarah to work on, or to explain the DC dynamics of the circuit.
I'm going to go ahead and request control. Okay, I think. Oh, cool. All right. Okay, so now that you know how we made our circuit, I'm going to talk about what happens when we apply a DC voltage to it under different conditions. And so Aaron already touched on this, but what's really cool about having a mechanical analog like the pendulum that we can compare to the Josephson junction is that everything we know about the pendulum, like energy considerations, can be applied to our circuit now. And so, for example, we look at potential energy. So here's the potential energy expression for a pendulum without any DC torque being applied to it. So it's just some constant times cosine theta. So for a Josephson junction, you have a very similar expression. It's some constant times cosine phi, where phi is the phase. And now if you do apply a torque to your pendulum, then you get this expression here added to your potential energy equation. And similarly, when you pass a current through your junction, or in our case, our circuit, you get this expression added. And when you plot your potential energy versus your phase, you get what's called a washboard potential. And the phase of our junction can be modeled by this point particle on the washboard, and its movement along this curve can help us understand different behaviors of it. So first I'm going to talk about the case when no current is being passed through our circuit or through a Josephson junction. So if you go back to the pendulum analog and you're not applying any torque to your pendulum, then it stays at theta equals 0, right? It isn't moving. And so if no current is being applied to a junction, then the superconducting phase stays at this potential minimum, or you can call it, like the bottom of the well. And so it's not moving. And if you look at the second equation from the Josephson relations, if it's not moving, then this expression, your d phi over dt is 0. And so your voltage across your device is also 0. But now when you do apply a current to your device, then this manifests as a tilt in the washboard. So basically, the more current you're biasing your device or our circuit with, the more your washboard tilts. And what happens is that you can keep tilting it, but eventually you'll tilt it so much that your little particle starts rolling down. And when it's rolling, what's happening? It's moving. Your d phi over dt isn't 0 anymore. And so your voltage across your circuit isn't 0. And that's when the circuit has entered the resistive state. And that's why in the IV curve here, can you guys see the mouse? I'm not sure if you can, but that's why in the circuit here, okay, cool. Thank you, Ethan. That's why you can see that jump from from 0 to non-zero voltage at IC. Cool. And so experimentally, we wanted to see this ourselves. We wanted our own VI curves. And so what we did is we applied a bias voltage over here, and then we measured our output voltage here and we plotted it. So comparing this to our VI curve from earlier, our I is really our bias voltage. And so we're going to be looking at the critical voltage here. And so you see that at the center where the curve is straight, there's no voltage going through it. And then you hit a bias voltage where you enter the running or like that rolling state. And that's when you see an output voltage. And similarly, if you start at 0 bias voltage and you ramp your voltage backwards and you hit negative VC or your negative critical voltage, then you see that shift or that change into the resistive state as well. And so next, I'm going to talk about damping effects, because it isn't just the differential equation for a pendulum that can be applied to our junction. It's specifically a driven damped pendulum. And so the way that we're going to understand damping effects with our washboard potential is by thinking of different levels of damping as different levels of friction along our washboard. And so in the case that your washboard is overdamped, that means that you have a lot of friction. And if it's underdamped, you have very little or no friction. So I'm going to first, or right now, focus on the case where it's underdamped. So
I think we may have lost.
not much friction.
We can't hear you anymore.
Hello?
Yeah. I think
You're good, Sarah. Go ahead.
Oh, okay. Where did I cut off at?
you were about to talk about how damping affects the switching and retrapping voltage.
Oh, okay, cool. All right. So say you start applying a bias voltage to the circuit, which means you're increasing the tilt of your washboard, and you hit the critical voltage, which is when the ball starts rolling, and you go beyond your critical voltage, so it keeps rolling, you're in the resistive state. But then if you want to ramp your voltage backwards to go back to your 0 voltage state, that basically means you're tilting your washboard back up. But the problem is, because there's no friction to help you stop that rolling, you can't just tilt it back to your original position to stop that rolling. You have to tilt it even closer to the horizontal, which basically means you have to get closer to 0 bias to go back into the 0 voltage state. from the resistive state. And I'll show you how that looks with data, and I think it'll like clarify it more. So here's some data that we took, and I'm going to start by asking you to pay attention to the red curve, which it's kind of hard to see the whole thing because the dark blue curve overlays it a bit here, but the red curve is like under there. But the red curve, it was taken when our Q factor was 2.54, so pretty underdamped. And experimentally, we ramp up our voltage, and we see around here that our circuit switches from the 0 voltage state to the resistive state. But now if we ramp our voltage backwards, you see that it doesn't switch back at the exact same location or the exact same bias voltage. You have to kind of get closer to that 0 bias voltage. So in other words, you're getting closer up to this horizontal position, or you're tilting it more. And that's what we call the retrapping voltage. And so now if you look at the blue curve with a Q factor of 28, that is way more underdamped. And you see that when we ramp the voltage up, again, switching occurred here into the resistive state, but then when you ramp it back down, you had to get really close to 0. That means you really had to tilt it up because there was way less friction to help that ball, to help you stop that ball from rolling, if that makes sense. And the last subtopic I'll be covering is thermal effects. And so even when your washboard potential is at the horizontal position and your point particle is down here, like I've been saying that, it just sits at the bottom, but there's always a probability of escape, however small. And that probability of escape from the well is proportional to your Boltzmann weight, the exponential minus delta U over kBT, where delta U is your barrier height and T is temperature. And so the temperature dependence here is really interesting, but it also makes sense because if you think about any, physical system or like a particle, which is what we're looking at in our case for this analogy, if you apply thermal noise to it, it'll become thermally agitated, and that extra energy can help it hop out of the well. And so that hopping out allows it to escape from the potential minimum that it was sitting at, move along the washboard, however gradually that may happen, and that means a voltage can appear across your junction. But the question is, how do we test this? We can't, I think Dr. Amet's words were, we can't just, take a blowtorch to our circuit. So what we had to do was use the concept of Johnson-Nyquist noise. And it basically says the RMS amplitude of thermal noise is proportional to temperature, or the squared of the RMS amplitude is proportional to temperature. And so, or effective temperature, I should say. So what we could do is create a voltage source, call it our thermal noise, and add it in with our DC bias into our circuit and call that our overall VB. And that's what we input when we take our data, basically. And so by changing that amplitude, we're like effectively changing the temperature of our circuit. And so now we have to talk about what we expect when we change temperature. So because of the temperature dependence and that Boltzmann expression and that extra energy that the particle now has, you don't need to quote unquote tilt your washboard as much as before to get the ball rolling, because that extra thermal agitation will help the phase escape out of the well. And so what that means is you're seeing phase slips, or you're seeing the circuit slip into the resistive state at lower bias voltages than at low temperature. But specifically in the underdamped case, because there isn't a lot of friction along the washboard to stop that ball once it escapes out of a well, you're entering that resistive state right away, which isn't the case in the overdamped. I'll get into it. But basically what this means in our data is that you see your circuit switch from the 0 voltage state to the resistive state at lower biases. And I'm going to pick apart this table a bit because you're probably wondering, why are we looking at histograms? Since I've been talking about probability this entire time, we had to look at the experimental probability that switching would occur at certain bias voltages. And so the way that we did that is by taking, I think it was 1400 VI curves at each effective temperature, and then plotting when the switching occurred for that temperature. And so each histogram is, 1400 data points, basically, like pieces of data. And so you see with the dark blue curve, that was like the coolest of these 4 effective temperatures. And you notice that switching occurs around like 0.75 volts mostly. And that was probably near the critical voltage of our circuit at the time, because at low temperatures, you're switching closer to critical voltage. But then as you increase the temperature, you notice that the histograms kind of, not kind of, they do shift to the left. And it shows that at lower bias voltages or at like less tilting of the washboard, you still see that phase escape thanks to its thermal agitation. So that's the underdamped case. Now, the overdamped case, I think, is a lot of fun. This one's my favorite. So because of the friction along the washboard potential with the overdamped case, when this phase slip occurs that I talked about earlier and your phase escapes out of the well, it could potentially, and it does, get retrapped in the next well because of that friction. And so as long as you're applying that thermal, that effective temperature, that thermal energy to your circuit, or to your junction, then it can keep escaping, but that friction is going to keep retrapping it. And so what does that mean? Well, that means because it's not continually rolling, that it never officially enters the resistive state super early, like in the underdamped case. But because your phase is still gradually moving, you see a small finite voltage across your circuit at bias voltages where you would initially expect 0 voltage. So I'll show you that with some VI curves that we took. So here, this blue curve is the coolest of the 3 effective temperatures. And you see switching occurs at around, 0.5 and negative 0.5 volts. But as you increase temperature and you look at the pink curve, even a little bit before 0.5 volts, you see like a little voltage appear there that wasn't there before. And then if you increase it even more, again, you see like an even greater finite voltage appear before 0.5. And this is what we call phase diffusion. And as Aaron mentioned earlier, another really interesting piece of data that you can get from these curves is the resistance of the junction. So if you look at the slope of these curves at 0 volts, then that gives you the resistance. And you see the slope changing, right? And so it turns out that the rate at which the resistance is changing is proportional again to the Boltzmann weight from earlier. And so you can check we wanted to check with our data to see if that held true, to see if the resistance at 0 bias was thermally activated, which means it's proportional to this here. And so what that looked like was we took a bunch of these curves at different temperatures. We numerically, differentiated this part of our curve, and we wanted to go ahead and plot it. But we decided, instead of working with, let me see if I can go back. Instead of working with this expression, that we could rearrange it, and by plotting log RT versus the inverse of temperature, you could get a straight line. And it's a lot easier to just like visibly see a straight line than try to, check an exponential, right? And so that first set of data that we took is the line that's the data points that are fit with the red line. And we did get a negative slope, which is what we wanted, because based on this, your slope is supposed to be proportional to your delta U over KB. But then we needed to check this delta U bit here, because So basically delta U is equal to 2EJ, and EJ is your Josephson energy, which came up earlier. We didn't really talk about it. But the point is, it's a characteristic of our junction or our circuit. And in our case specifically, you can change that value of EJ by changing a resistor in our circuit. And there's an equation that's not important right now, but we checked the equation and we wanted to know what resistor value would give us an EJ that was 2/3 of our original EJ. And so we plugged in that resistor, we retook the data, and we wanted to see if our slope would scale accordingly. Would we get a slope that was 2/3 of the original slope? Because if we did, that means that this is right, or at least it's right for our data. And so that's what we did. And we actually got, I think it was a slope or a scaling of 0.6, which is pretty good. I was happy with it. And yeah, so that was my last bit. And I think here I pass it on to Brian. He's going to be talking about what happens not only when you apply DC, but AC voltage to our circuit.
Thanks, Sarah. So as Sarah said, we are now, hold on, there we go. We're now going to be applying an AC and a DC source across our junction, and that's called the inverse AC effect, or that's the regime where we see the inverse AC effects. And so for our junction, we apply an AC and a DC voltage across it, which simulates a current across our junction. So for anyone that was getting tired of the pendulum, don't worry, we're going to keep using it. But the reason for that is with the junction being described by a macroscopic quantum wave function, which with its phase being phi, there's a lot of counterintuitive things that happen in the junction, particularly in the inverse AC regime. But again, as has been said before, the pendulum analogy helps us understand a lot more of the things that are going on. And again, you can see this is the equation of a driven pendulum, and this is the equation of our Josephson junction. So whereas in a pendulum you have a DC torque and an AC torque, now we have a DC current and an AC current, or in our case, a DC and AC voltage. So to start off with, we have some simulations. This is going to be a simulation of a phase-locked pendulum with an AC and a DC torque. And so what phase locking is when you have your periodic driving force on it, for every one period of the driving, there's a certain fixed number of oscillations that your system will undergo when it's phase locked. And so in this case, we have one full oscillation for every driving period. And systems like the pendulum and the Josephson junction really, to anthropomorphize, like to be phase locked. And so if you deviate very slightly away from its phase lock state, it really likes to stay in that phase lock state and will kind of resist changes to that. So we have a time series of a theta dot, the angular velocity from our simulation. So the top one is actually the time series from the simulation you just saw. And so with Josephson junctions and with the pendulum, the oscillations, particularly in the junction, happen so fast that when you're analyzing the values of your output voltage experimentally, you always take the average. It's too very fine-grained, and you can't get the detail that you would necessarily need to without averaging. So you can see this orange line here is actually the average of our angular velocity, and you can see it's somewhere around 7.5, and that's with a DC torque of 0.5. Now, all the other parameters are fixed under this situation, but you notice that you have a DC that's slightly higher. And now the average here is about exactly twice, as a matter of fact, of the average that you have here. And so what this is indicating is keeping everything else the same. When you vary your DC input, so for our junction, the DC voltage, the angular velocity, the average angular velocity doubles, and you actually get double the amount of oscillations in one cycle of the driving. So returning back to the simplified version of the circuit again, it's just to reiterate that the V out that you get across your junction, or in our case, the average V out, is going to be proportional to the average phi dot for our junction's phase. And so turning back to the phase locking with the pendulum, what does that correspond to in our circuit? So these are experimentally derived graphs. And so we, again, just like we had before, we fix all the other parameters except for our DC voltage across our junction. And so you can see here, for a given DC voltage across the junction, we have our average V out or slightly above 500. And so we're going to call that kind of like our fundamental right there. We have it at n equals 1. And when we vary V out and we increase it, or sorry, DC voltage, V out doubles again. So that's where, just like we saw before, we correspond to doubling the average value that we have out. And the same thing for 3. So this would correspond to 1 oscillation, 2 oscillations, and 3 oscillations for our pendulum. But of course, this is for our junction and the phi dot, the phase of our junction. So this is where you get something called Shapiro steps. And so going back to the IV curve, I think it was mentioned in some of the slides with Aaron and Sarah, an IV curve gives you a lot of detailed information that that you would be interested in for a circuit. So this is a very basic ohmic curve. This could be for a circuit where you have a battery, wires, and a light bulb maybe. And so something you could get from this would be the slope will help you understand the resistance in that circuit. So this is kind of a very basic one. Now, turning over here, this is experimentally derived from our circuit. And you can see it's quite a bit more detailed than this basic version. So again, corresponding down here, you have a DC current in our circuit that's simulated by a DC voltage. And this is the average voltage that we just saw in the figures that we just had in the prior slide. And we've normalized them. So again, remember that this corresponds to a multiple being multiplied by our average phi dot. And so just like we had with the pendulum, when it becomes phase locked, it likes to stay in that phase locking and will kind of resist perturbations. Right here, when it becomes phase locked, when the AC frequency of our AC voltage across the junction becomes phase locked with phi dot, you get this locking here. And as you deviate and change your DC voltage across it just slightly, it wants to resist that change. And so that's where you get these plateaus from, until you eventually hit a point where it's allowed to jump to the next one. And so these are 2 different curves that correspond to 2 different AC frequencies. And this is exactly what you'd expect to see based on theory. So that really shows that our circuit is simulating this phenomena very well. And so turning to differential resistance. So differential resistance, all that means is the rate of change of your output voltage with respect to your current, or in our situation, input voltages. And so VC is just a way to normalize these input values. And so on these maps, a given point corresponds to a unique DC and AC input across your junction. And the left figure here, which you can see is a little bit blurrier than the one on the right, was actually generated by data that we gathered from our circuit experimentally. And the right corresponds to a numerical simulation based on the Josephson equations that you saw earlier. So again, you see a striking similarity between experiment from our circuit and theory. And so what exactly do these maps represent? Well, for this vertical cross section here, which corresponds to a fixed AC voltage across the junction, as you scan across, you're changing the DC voltage values. And what the colors correspond to are different jumps in voltage. So the darker regions here correspond to 0 jumps in voltage or constant voltage, and the brightest yellow correspond to the steepest jump in voltage. So you'll notice if you fix AC voltage and scan across, you encounter some of these jumps here. And so actually one vertical cross section corresponds to 1 Shapiro step curve that we just saw. And so we actually created an animation that shows you, as you scan across, the evolution of the Shapiro steps. So you'll notice as you go further and further to the right, you start to get more and more of the Shapiro steps. And eventually, as you scan further to the right, you see it starts to get jagged and kind of messy looking. That's where we start to encounter some chaos. And that's where we're going next. So you might have heard the analogy, a butterfly flaps its wings in one part of the world and leads to a chain of events that causes a hurricane on the other side of the world. And so really what that analogy is trying to get at is, in chaos theory, you have a completely deterministic system. It has some set of equations that completely govern its behavior. So maybe Newton's laws, for example. But the system acts in such a way that very small changes in initial conditions over time will lead to behavior that looks completely unpredictable. Your initial conditions will not seemingly be able to predict what's happening in the long run. And that's the hallmark of chaos. So here's another simulation. In this simulation, we've set our parameters such that the pendulum is in a chaotic state. And so you'll notice, even though it's governed by the same equations that we showed earlier that are completely deterministic, it looks like it's kind of just moving around completely at random, kind of chaotically. And so going back to the time series we had before, the top one corresponds to our phase locked n equals 1 state that we showed previously during our phase locking slides. But now the bottom one corresponds to the time series under chaos. And you can see it's much more random looking and kind of, there's no set patterns to it. And now you see on the right, the corresponding fast Fourier transform maps of it, so the frequency spectra. And you notice for the phase lock state, you have a very low background of frequencies other than the sharp peaks in kind of your fundamental, which would be this peak right here. And then you have some harmonics and subharmonics as well. But now when you get to the chaotic state, notice that because this motion is so chaotic, it has to be composed of a lot of different frequency values. And so you get a very, very dense amount of frequency, and the amplitudes of them, even for the background, now spike and kind of wash out some of these other peaks that we used to have. And so the frequency maps are going to become particularly important in the rest of the discussion, because they give us a really nice tool to be able to show us when we have kind of normal periodic behavior, phase lock behavior, period doubling, which we'll talk about, and particularly when we get to chaos, because when you have a very kind of like dense frequency spectra with a high background noise, we know we're kind of somewhere in the region of chaos. So this is kind of experimental data gathered from our circuit. And this is in the underdamped junction. So this is when you're underdamped, that's going to be where you're more likely to see some kind of chaos, because damping will kind of damp out some of those effects. So now we're in the underdamped regime. And so this, what this map actually corresponds to is a vertical cross section corresponds to one of those frequency spectrum maps. So you'll see here, this bright line is our fundamental. That's our highest peak that we had before. And as you can see, as you scan across different DC values, you start to get a lot of different behavior. And so what that change in behavior is in terms of nonlinear dynamics is called bifurcations, which just means qualitative behavior or transitions between different behavior in your system. And so you can see here we have just our fundamental. If we look at this cross section here where it's phase lock, we see we have a fundamental and we have a subharmonic over here. But these big bands right here correspond to chaos. And just like we saw before, when we have chaos, that, remember this being a one band of our frequency spectra, that's where you had that really dense background noise showing up during chaos. So that's where you can kind of see, okay, here's our phase lock state, here's our chaotic state. So this is a very nice tool to be able to see what parameters are going to cause us to start transition to chaos. So zooming in on this region right here, this gives us a little bit of finer picture of what we were looking at. So there's different ways to transition to chaos. One, for example, is period doubling, which this is actually not from our data. This is a very classical diagram from chaos theory. It's called the Feigenbaum diagram. And so what happens here is you have just one fundamental, then you have period doubling. It splits into 2, 4, and it kind of rapidly starts to period double to chaos around this region, though you have some intermittency where you have some periodic behavior again and then transitioning back to period doubling at chaos. So that's that. Even though this doesn't correspond to the same system, notice with our frequency spectrum map, we get some similar behavior. We start off with that one fundamental peak right there. Now we start to get a subharmonic. We start to double that periodicity. And now we start to hit into some chaotic bands, but then we transition back into some periodic behavior again. So it's very, very nice to be able to see kind of some transition between chaos, since there's so many different ways to transition. Now, this is, again, another frequency spectrum map. This is going to be in our overdamped regime. So where we had a ton of chaos before in our underdamped, now we're in an overdamped regime where we're less likely to see as much chaos, or sometimes not at all, depending on how damped we are. So now what you can see here is with this, we have just one cycle. So that would kind of correspond, if you're looking at a time series, to just a nice sinusoidal wave with just one peak per period. But here, this is where we start to get that period doubling. This is called a 3 cycle. You'll notice there's 1, 2, 3 peaks. And that corresponds right here to 1, 2, 3 peaks because we have our subharmonics down here. This is going to be a 2 cycle because you have 1 and then another subharmonic. And over here, it might be hard to make out, but this is actually a 5 cycle. So you'll have 5 harmonics there. And so this is a zoomed in picture. And so what you'll see is actually, there's a lot of self-similarity if you zoom in. So you have that main band right here, and we start to get a lot of self-similar structures kind of emerging if you zoom in on our fast Fourier transform map. So fractals. So there's a famous fractal known as the Devil's Staircase, and that's actually this main band that you see here. And it has, fractals typically don't have integer dimensions like you would have for 2 and 3 dimensional objects. They have fractional dimensions, and the Devil's Staircase is well known to have a theoretical dimension of 0.87. And so taking that main band and isolating it out here just in this curve, notice it looks a lot like our Shapiro step curve, right? And so for particular parameters, this Devil's Staircase structure actually presents itself. And again, with fractals, a common feature of it is something called self-similarity. So this is the full curve, but now notice if you zoom in on this jagged region, you get something that starts to look like it again. And if you zoomed in on that region right here, you would start to get it again. And so this is a different type of fractal known as the Sierpinski triangle. And so this kind of animation shows you kind of that self-similarity. As you zoom in, you repeat that structure over and over and over again. So we're in some preliminary results right now for this fractal dimension. We're still trying to extract the Devil's Staircase 0.87 dimension from that figure you saw before. But this is just a recent thing that we've been working on. So some preliminary results, we took that Sierpinski triangle, and this is how you calculate the dimension. I won't really go into that unless someone has questions later. But the Sierpinski triangle is well known to have a fractional dimension of about 1.58496. And our initial preliminary results here show you that our linear regression yields a slope within that with that value within our uncertainty. And so lastly, we've been talking about a lot of different phase space diagrams like the frequency spectra to kind of show you how we transition in and out of chaos. But in doing so, we've really kind of limited ourselves to fixing every other parameter except for, in the diagrams I showed you, varying DC voltage across the junction. But there's a lot of different parameters that go into this. And so we'd like to be able to see how our system transitions in and out of chaos while being able to change more than just one feature. And so what you see here is another map, just like we had before, where one band corresponds to a frequency spectrum and a normalized DC voltage on the bottom. So nothing particularly new there. But up here, we actually have a second 2-dimensional aspect of phase space. So really, if you wanted to think about this, we have 4-dimensional phase space that we've kind of reduced down to two-dimensional figures for it. And what we can change here is something called the bias frequency and the damping coefficient. So as we go across here, to the left, you'll have less damping, and to the right, you'll have more damping. And so what we did is we created a simulation that will actually show you as you swipe across here to different damping. So now you're in the overdamp regime. You're not getting a ton of chaotic behavior. You have your fundamental frequency and some period doubling occurring. But now once we get into this red region right here, we're starting to get less and less damped. And you can start to see we're starting to get some of these bands of chaos forming at different voltage values. And now right in the middle, where we're starting to get less and less damped, we're starting to get these giant bands of chaos. So this is a really nice way to, like tool to be able to show you different parameters where you're going to transition in and out of normal periodic behavior, period doubling, and chaos. And that is the rest of my discussion.
Right. Thank you.
Thank you, Aaron, Sarah, and Brian for your talk. This was a ton of data, and congratulations on the amount of work you have accomplished together. I'm going to open the floor for questions. Yes, Lauren, go ahead.
Hi, yeah. So at the beginning, you kind of talked about these superconductors. I was just wondering if you could talk a little bit more about kind of how you got these superconducting materials. I don't know very much about them. Kind of like what it was like to kind of like work with them.
Maybe I'll take that one. So we have an apparatus at App State in room 267, which is called a sputtering system. And that's a system that allows you to evaporate thin films of any metal you want. And in particular, we can evaporate superconducting thin films. And so a lot of the research that we've done over the past years or few months is fabricating devices with superconducting electrodes. And superconductors are actually much more common than you would think. For example, aluminum or lead are superconductors, right? So they're very common materials. So then it's just a matter of making devices with them. And so we have a set of fabrication techniques to pattern electrodes with those materials. So that answer your question a tiny bit? Or?
Yeah, cool. Thank you.
Any more questions?
Did you take data points from the circuit? Like what's that, the data acquisition system?
Yeah, we just used a DAC board actually, which was pretty great. We switched to, at one point we were interfacing with an oscilloscope. We were taking time traces from that, importing them into Python and working with them. And now we're using a picoscope, which is like I don't know what you would call it, like a virtual oscilloscope, kind of like it's still like a device, but just like not as chunky as your traditional oscilloscope. But yeah.
Yeah, I like picoscope. I've used those before.
Yeah, picoscope is great. I'm a big fan.
Laptop into an oscilloscope. Yeah,
Wait,
that's
what was the last part?
well, it kind of turns the laptop into an oscilloscope.
Yeah, exactly.
Yeah, they're nice. And then you got all the data already on your laptop.
Mm-hmm. It's like you adjust more stuff. Yeah, it's really cool. But
you apply noise as AC, and then you apply an AC drive. Like, is the difference just the amplitude and the frequencies? They're both applying AC to the DC, like summing.
wait, say that again.
So what's the difference in applying noise?
Oh, okay.
What the third part of the talk was, applying AC.
So I guess I'll let Brian talk more about the AC, but yeah, it's a matter of we sent in a frequency as well with our lock-in, and that was the main difference. Like whereas with our noise, we just put in an array of voltage values from a Python program with a Gaussian distribution to just mimic white noise.
Okay.
Perhaps one way to think about it is if for the AC voltage, it's a single frequency, right?
Yeah.
It's applied by lock-in, whereas for the noise, it's white noise, so it's like random fluctuations with a spectrum which is flat, right? There's no particular frequency. It's like a white noise distribution, so look more like voltage fluctuations.
Okay. Yeah, I didn't pick up on the noise being white noise. I thought it was just one frequency, so I didn't see the difference. But
oh yeah, I didn't specify, so.
yeah, now I get it.
Yes, Ethan.
So I actually have two questions. First of all, what led you to investigate like the fractal nature of Shapiro steps? Was that something that you just noticed and decided to look into more, or is that a like what led you to the Devil's Staircase specifically?
So yeah, so basically we measured it experimentally, and then Brian got very excited about all those fractals and forced us to look into that in more details. Am I summarizing things properly, Brian?
Yeah, I think so. Yeah.
Yeah, that was really cool.
Yeah, so Dr. May was starting to get into, I came in on the latter half of the research, and Dr. May knew that I had done stuff in chaos theory and nonlinear dynamics, and they were starting to get into that and he was taking those FFT maps that you saw, where you start to get those double staircase structures. And it's actually kind of well known that the double staircase fractals can appear in certain regimes for the Josephson junctions. There's actually a lot of papers on that. Yeah, because I have a particular interest in chaos, I've been really pushing to get some fractal dimensions and look at the different kind of fractal structures and stuff.
Can
Right.
someone please?
Okay, thank you.
Do we have more questions? I have a question of my own. So my understanding is that the case for overdamped and underdamped state is associated with the, like, from the device point of view, it's either the presence or absence of the shunt, right? How did that play into the AC measurements that Brian showed, or the simulations?
I don't know who's controlling the PowerPoint right now, but could you go maybe to the simplified circuit slide? So the quality factor was going to determine whether you underdamped or overdamped. We control it by changing that resistor R, which is, that shunting resistor, which is in parallel with a voltage control oscillator. It basically, there's a formula that maps the resistor value to the quality factor. So by changing that resistor, just to connect a different resistor, you can change the Q factor. So there's always some damping, right? But we can we can vary from quality factors of about 0.1 to about 30 just by changing that resistor. So it's really nice from a measurement standpoint, because historically we've been doing more like nanofabrication, and when you make a junction, so the geometry of your device that you spend 2 or 3 weeks making is going to determine the quality factor.
Right.
So it's impossible to change it. Whereas here, you just connect something different and get a different quality factor, which is
So I'm thinking, if, let's say, if you made a real Josephson junction device and you were in the ultra cold temperatures and doing the measurement, will it be possible to, I mean, any device will have some shunt resistance, right? So will it be possible to reproduce the simulated data that Brian showed in, considering that any real device will have the shunt? So will it be possible to explore the underdamped and overdamped conditions with that precision and control?
So yes. Now the issue is with our system. So the natural frequency of the junction is a few hundreds of hertz by design. So that means that we can see, all those frequency spectrum maps that Brian showed. We can measure them with an oscilloscope, and it's, from an oscilloscope point of view, it's really, I don't know if I can say easy, but it's very doable, technically speaking. But for if you make a Josephson junction from superconductors, like a real device, that typical frequency is on the order of a few gigahertz. So it's not like you cannot record the oscillations of your voltage across your junction and then get the frequency spectrum of that thing, because it's so fast.
Right.
I don't think, I wouldn't know how to measure it for sure. So it's much easier. So the reason we're able to get that level of control and that precision in the frequency spectrum is because all the frequencies are some orders of magnitude slower than in a real device, which is kind of nice. But there are some observations in some papers out there of subharmonics and things like that. It's just a lot less pretty than our stuff, because there's it's harder to measure.
Thank you. Do we have more questions? If not, let's thank all. Okay, yeah, yes, go ahead.
Oh, sorry. Oh, hi there. Hi, everyone. Yeah, this was a great talk. For people who don't know, I previously used to work for Dr. Amet, and right now I'm at NC State. So I had one question regarding the phase lock oscillator. mechanism that you presented. The reason I found that interesting is because all these oscillators, they probably have the same phase and they're oscillating at the same phase. And that's very similar to a model in mathematics, the Kuramoto model,
So
which
what?
basically the Kuramoto model.
Mhm.
And that describes synchronization of all these individual oscillators. And we kind of see that in the optics that I'm studying right now as well. And that leads to basically the phase building up, synchronizing, and then dying out again, which is similar to stuff that you presented where you have regions of chaos and then a system where it's behaving systematically as well.
Mhm.
So have you looked into this?
So I guess the short answer is no. but thank you for bringing that up. Something that maybe didn't come across in the talk is that you may think of that phase locking as something specific to that type of differential equation and some rather tricky detail of one particular equation, but it's really not. So thank you for bringing it up, Yash, because synchronization is everywhere in any type of system. So for example, you have biological systems that
Right.
exhibit synchronization. I'm not going to detail them because my last biology course was 15 years ago. but yeah, there are plenty of different systems across physics, biology, even chemistry, as I understand it, that displays the same type of phase locking behavior. So it's something that's actually extremely common. So.
And in fact, I think I've even seen this model being applied to Josephson junction. So maybe not in the same context, but I've seen the same model being applied to Josephson junction.
Ethan, did you raise your hand again, or is this from last time?
Yeah, I had a second question that I just sort of wanted a little bit of clarification on.
Please go ahead.
So the noise is simulating thermal energy, right? And the DC bias is just your normal bias across your junction, right?
Mm-hmm. Yes.
Okay, I was just double checking. So you can, yeah, I guess in a normal one, the thermal energy is also like, it does directly affect the voltage. So it makes sense that you can just wire them together like that. That's just not something I'd considered. It's an interesting approach.
Any other questions?
I think that was the last of it.
All right.
Okay. Do we have more questions? If not, let's thank all the speakers for a wonderful talk, and wish you all a wonderful weekend. And we will meet again in fall in the next Colloquium series. Goodbye.
Thanks, everyone.
Thank you for the talk. Have a good weekend.
Thanks for attending, everyone.
Yeah, I enjoyed it. Nice talk.
Oh, thank you. Was it? Oh, I gotta ask him if it was worth missing the tires.
Oh, yeah, great.
Oh,
That
there
was-
he is. I thought you left. Yeah, was it worth it?
That was very good. Yeah, excellent.
Okay, awesome.